Go, Mike. There we go. Excellent. All right. So remember last time I kind of mentioned something about implementing all of the instructions and do it in small little programs. Okay. So let's check out the Google Drive. Okay, because I put everything into the Google Drive. Okay. So. Okay. Are you guys doing okay or? Yeah. Okay. Because you're blocking the all right. So I'm going to the Google Drive and under 310 shared processor. There we go. So I added just one file. It's called opcos.tar.gz. You can see that as well. Okay, if you want to download it, you can download it. If you have any more additional homework regarding the opcodes or the implementation of the microcode for the toy processor, so you're more than welcome to download this file, take a look, just mess around with the program and use it as a template to implement additional opcodes if you want. Okay. So what I'll do is I'm going to download this. I just want to show you, how it works in case you want to use it for any purposes, and also just how to use it, because once you know how to use opcodes.tar.gz or the opcode generator programs, it really helps to make it easy for you to test the instructions. And when you test the instructions, it really helps to understand the material in this class. For instance, okay, what is indirect addressing mode? Okay, this is indirect addressing mode, but what is being done inside the processor when you try to access a memory location where a register points to it? Okay, so that's what I'll do next. Is I'm just going to download this file, unzip it, so that we can all look at the content. Okay, save file. We can do it inside the processor folder. Okay, save it over there. Switch back to a command line prompt. Go to processor. There we go. Okay, so once we get to the folder containing the tar.gz file, if you try to do this in Windows, Windows natively does not know how to handle a tar.gz file, so you will need to download 7z. Okay, one of the programs you can use is 7z or 7zip. And that program can handle tar.gz files. You can also unzip it inside the Linux virtual machine that you got like really early on in the semester. And the command to deal with this is xzvf. The V part is optional. It means you're verbose. And then just give it the name of the tar.gz file. And it will give you a list of all the files that is created as a process. So you go to the opcodes folder, and the green ones are the actual commands. They're already compiled, and you can see that I have individual commands to do, to implement each instruction. Okay. There are two files that are utilitarian, okay, or three I should say. One is ucode.c, and this file just basically defines a certain bit field structure thing. So the way I did it was okay, you can see it. Turn off syntax highlighting. Now you can see it. So the way I did it is I represent the width of each field, okay, which is the first column, and then the second column is the offset in terms of number of bits to shift to get to that column. And then the last one is really just a string to describe what it is. Okay. The actual program that I have do not make use of the first or the last column. Okay, I did not actually make use of those, but they are available nonetheless. Okay, just so that if we need to do something about those, that the information is there. Okay. And then we have read-rom. Okay, read-rom is a program, but the actual code is parse-rom, which is in a program called, or in the source file called rombin.c. So in rombin.c, this is parse-rom, which is a little bit big because I have to basically understand the format of the ROM file. So, okay, just a quick thing. Okay, so what it does is it uses the fgetS command to get a string with including the terminator, the end of line character, which is the line feed character, and it will compare that to this string here. This string is at the beginning of every single ROM file, so I'm just using that to check, okay, to make sure that the file I'm reading is one of those files. If it's not, I'm just going to stop right away. So the main parsing part is down here. So this is the main parsing part. I'm using a state machine, or kind of a simpler state machine, to do the parsing. I'm reading one character at a time, find out what it is, and use it to point me to a state, okay, in the state machine. And then in the state machine, I will look into, okay, what kind of character is this? Given the state I'm in, and given this is the input character, what should I do with this character? Okay, and that can trigger a state change. For instance, if I've been parsing a number, reading digits, and then suddenly I see a space character, that would change the state because I'm done reading a number, and I'm now moving on to the next number. Okay, so this is the parsing part, which is a bit long because it is actually kind of complicated in a way. So it's about this long. Okay, so this is all the code for parsing a ROM file. And then this part here is bin to ROM, which means I'm looking into an array of slices, and this is how I generate the actual output as a ROM file. So I have a way to read in a ROM file and parse it so that it becomes an internal representation. 4,096 locations, each one is 32-bit wide, because I cannot allocate 26-bit wide fields in C. I suppose I can, but it doesn't make sense to do it. Okay, and then this one will do the reverse. You give it a chunk of memory, 4,096 locations, and it will crank out. It will output the ROM file as a result. Is that okay? So these two are utilitarian functions that I use for each program. Read it in, do some processing, and then output. Back to the other program. Okay, ucode.c. So read ROM is really just the same thing as parse ROM, except it will also initialize a global variable that is global to this particular file. When you see a global variable with a static in front of it, it means the name, in this case just ROM, is only visible within this file. Even though it is quote-unquote a global variable, it is not global across source files. It's only global within this file. The next one is write ROM, which is really just a mirror image of bin to ROM. So the slicing one is this one here. Okay, it is this is the most complicated one. Okay, because I'm passing an array called slice, and in slice it specifies the actual value for each column in the spreadsheet. Okay, I'll show you how it is used later on. Opcode is the actual opcode. And then the most interesting part to me is the XX offset and the YY offset. Because those two are indicating, do we specify register XX, do we specify register YY? If so, those will be the number of bits to shift into the opcode. Okay? And then we have the offset here, because some instructions require more than one slice. Most instructions require 2 slices of microcode. So the offset is for me so that I can generate multiple slices corresponding to the same opcode. Is it okay so far? Kind of? Okay. So the code in here is just, it's not too long, but it does make use of some kind of nifty tricks. So that if I do specify an instruction that has XX to specify one of the 4 registers, this code will actually crank out 4 variations of that instruction. If I have an instruction that has XX and YY, this will crank out all 16 variations. And it knows where to put the register X and where to put the register Y because of the parameters XX offset and YY offset. If an opcode does not have any type of registers, like no op or halt or instructions like that, then XX offset and YY offset will have a value of no XX or no YY as an indication that no, this instruction does not make use of registers. Do not crank out multiple copies of this. Is that okay? All right. So given these utility programs or utility functions, each program, like no-op, is really just consisting of a gigantic array. Well, not really gigantic, but in this case, it's a 2 by 18 array. Okay, num slices is just 2, so it's 2 by 18, and then I just have the individual values from the columns of the spreadsheet. Is that okay? The actual program is only this long. This is the main function. Read it in from standard in, put the slices in, and then use breadcrumb to output the result. So every program looks kind of like this. The only difference between the programs would be the opcode itself, which is here, whether it takes a register X, whether it takes a register Y, and also the offset. I think all of the instructions that I have 2 slices, with the only exception of the halt instruction, which only has 1 single slice. Okay? So some of the instructions are a little bit cool. This is a fairly typical example. So when you look at these values in slices, 0, 1, 0, 5, 0, 0, 1, 1, and then y, underscore field, 1, and so on and so forth. These are the exact values from the spreadsheet. And I found a very easy way to copy and paste from the spreadsheet into a text file. You just select the cells inside the spreadsheet, Control-C to copy, go to whatever editor you want to use. Okay, I use VI, but you don't have to use VI. You can use mousepad or notepad or whatever. When you paste, the individual values will be tab separated using tab character. So what you do is then on that one line, you replace all the tab characters with commas, and you're done. Okay? The only thing you do have to modify is to locate where you specify the registers. We potentially have 3 selections that are register based. Okay, we have register bank output 1 select, register bank output 0 select, and register bank input select. So those are the only 3 fields where it can be parameterized. So in this case, I use a very specific value, which is actually negative, to represent that this is actually not a constant value. This has to be parameterized and be instantiated based on register values. And that's it. So once I have the basic structure done and test the simple program or test the simple instructions to make sure that it does work, the rest is really just copying one source file to the next, just tweak a few things, and then move on to the next one, and so on. Yep.
Let's say I try to write a program like this. Where would you start?
I start with how I want the collection of programs to work in the first place. So in this case, I can show you guys how that works. So there's also a make file here. Okay, so let me show you the make file, which is something that I hope we can get to. Okay, so the make file is a text file that basically states the dependency of the individual components. So in this case, all is called a target, and then these are this is the dependency. So in order to quote unquote make the all target, it needs the executable no-op CPR, which means copy register, LDI load immediate, load, add, subtract, rotate. This is a right shift, not and or compare. ST is store, JC is jump only if the carry flag is 1, and then we have the other ones too, unconditional branch and halt. So all of these are executables in order to quote unquote make the all target. Is that okay? It's just a little shorthand, so I don't have to say make no-op, make CPR, and so on. I can just type make all, it will generate all of the executables. And then with each one, no-op depends on the object file no-op.o, romb.o, and ucode.o. Okay, I could have use a macro so that I don't have repetitions of romb.o and ucode.o, but I was just too lazy. Okay, it was already at 12 a.m. this morning, so I kind of felt like, okay, I can just copy and paste a few times. I know this works already, so it's not the best or the most elegant code, but it does work. The rest of this file can be a little bit complicated, especially when it gets down to here. Okay, send off. So when it gets down to here, especially this stuff here, it is a mechanism to auto-generate the dependencies. In other words, this is using a mechanism in GCC so that GCC can automatically figure out the dependency of a .c file on header files. Even when it is nested, it will figure it out. So this way, I don't have to track dependency between .c files and .h files anymore. I leave it up to GCC to handle that. Okay, so that, which also means if I make a change to the header file, it knows what to recompile to bring everything up to date. Okay, all right. So let's go ahead and take a look at. It leaves all the object files behind. So one way to make sure that everything is up to date. Let me see if it will do that. Yep. So now we have just recompiled everything, and let's just run one of these commands and see what happens. There is a special file in this folder called empty.rom, and when you look at the actual content, this is actually hand edited. This is the format of the ROM file. The first line always says it'll be 2.0, which is the version of Logisim that we're dealing with, and then raw means it is not, I guess it's just spelling out the bit patterns. And then it uses the count, which is 4096, and then the multiplication symbol, the asterisk symbol, to mean, okay, what values are we repeating? Okay, so we are repeating the value 0 4096 times. Now the interesting part about this is the count part is in base 10, but the actual value part is in hexadecimal. In case someone has looked into this file, you would notice that some numbers are in decimal and some numbers are actually in hexadecimal. So the parsing subroutine that I have can handle that too. All right, so here's the.
So that's a 0 in hex.
Well, 0 is 0 regardless of whether it is hexadecimal, binary, or base 10, or base 16, or base whatever, right? 0 is just 0. So let's see what happens when I run no op. It requires an input from standard input file. For those of you who are not familiar with that term, standard input file, it is cin basically. It's what cin is representing. Is that okay? Does everybody understand what I mean by cin or the standard input file? Okay. So I'm going to give it empty.rom as the standard input file, and this is the actual output. The actual output is from here to here. Okay, so let's take a quick look at what it means. Okay, the first part is really just identifying what file it is, what kind of file it is. 1080007. Do we recognize that? It's the first slice of the no-op instruction, and then the second one is E80004, which is the decode part, so that the next instruction would actually branch to whatever slice is corresponding to the opcode that you want to execute. Is that okay? All right. So this is the output, okay? This is the actual output of a particular command. So what I can do now is I can say, okay, no op, okay, I can do this, cat empty.rom, okay? Cat stands for concatenation. In other words, it allows you to specify any number of files, and it will just concatenate the content of all of these files. And then the output is always going to standard out, or standard output file. For those of you who are familiar with C++, it's cout. Okay? So cat empty.rom doesn't do anything particularly exciting. It's the same thing as type, the command type type in DOS. It just shows you the content of the file in standard output. So it doesn't seem like it's useful. But what I'll do is I'm going to pipe this to say no op. Okay? So the pipe symbol, or the vertical bar symbol, is a pipe symbol, which basically means the standard output from the first command becomes the standard input of the second command. Okay? So let's see what is the result of this. Okay? Okay, dot slash, because it is inside this folder. There we go. Okay, we have seen this before. Nothing new, right? Because the output of no op is just this part here. But now I can use the same method and say, oh, take the output of no op and do, let's pick the next one. Which one do you guys want to do? Let's do something that we are familiar with. Halt. Halt is the easy one. Halt doesn't actually do anything at all because it just wants 0, all zeros in those locations. Let's pick something that you have implemented recently. Compare. There we go. So now the output is a little bit more complicated because it is combining the no op output here, skip a whole bunch of locations, and then we have the 16 variations of the compare instruction. And for each of the compare instruction, it consists of 2 slices and then 14 zeros until we get to the next slice. Yep.
So did you write your own compiler right here almost?
Not quite. I mean, this is really just a generator to generate the microcode. Okay. In other words, if I keep doing this, okay, compare, jump, oops, pipe to LDI, pipe to LD, pipe to not, okay, and so on. It will keep piling more and more microcode for those instructions. Is that okay? And so you guys are more than welcome to download this. If you want to play with it, play with it. But now I have the means to basically look at the ROM file that you turn in as homework assignments and integrate your implementation of the opcode into the implementation of all of the other instructions that I have supplied. So let's say your homework assignment is the compare instruction itself. I would use my code to generate every single other instructions and only include your version of the ROM file for the last one. Is that okay? All right. Okay. So are there any questions about the use of microcode from the previous two classes? We lost the recording for one, but I think we made up with the previous class, which was recorded, and I used an example to illustrate how to use the instruction of the toy processor to write simple subroutines. Are there any questions about all that stuff?
So this is on Google Drive?
This is on the Google Drive. Yeah, so the tar.gz file, the opcodes.tar.gz file, is in the same Google Drive folder as the rest of the documents. Okay. Now, one thing I haven't really tried is to have this format here and have it read back in Logisim. Just because I think it is the right format doesn't mean Logisim will think the same way, because this is just one single long line. If Logisim is not smart and just use a buffer of 255 characters, it probably won't handle this. So it's a good time to test it. I'm just going to test this. We capture the final output to, let's say, opcodes.rom. Okay. So now when we look at opcodes.rom, oops. Yeah, opcodes.rom. It is two lines. Okay, the first line is version 2.0 raw, and this is the second line, which contains all of the specification of those instructions. So now we can use Logisim and take a look and see whether Logisim can handle this or not. So java.jar downloads Logisim, and we'll open up the processor from the previous time. So it's going to be processor.circ, where the ROM component is located. And then what we'll do is we go to the ROM module here. Okay, this is correct. We go to edit content, and then we say open. Go to the subfolder opcodes, locate opcodes.rom. There we go, and say open. Uh-oh. Yep, there we go. So it's got it. Okay, it was able to read the actual content from the ROM file that I generated. This is the last part that I didn't check last night, because by the time it was done, it was like 1 a.m. and I still had a very long conversation to do with my daughter, so I didn't have the chance to actually test it in this case. So, are there any questions about this tool here? Okay.
Is it supposed to be every other line there?
It's only displaying 8 bits across, not 16.
Correct. Yep. Good observation, because it goes from 6F0 in this case to 700, because each row only has 8 items and not 16. Yep. Okay. Any questions? No questions? Did anyone else finish implementing all the instructions into a ROM file? Okay, so some of you did. So you can compare my implementation to yours. Actually, what I'm asking is check my implementation. Make sure it's correct. Now remember, some of the fields are don't care, which means the actual slices can look different, but functionally they can be still the same. In other words, for instance, when an enable pin is turned off, then it doesn't really matter what you do with the other pins because the device or the individual component is turned off. So you can keep that in mind. But I did check all of the opcodes across against. Okay, I did check everything against the. Okay, what am I saying here? Against the spreadsheet itself. So when I compare everything against the spreadsheet, which is microcode worksheet, they all match. So I have I would say reasonable confidence that it does work because it does match the last column of the spreadsheet. Yep.
I do have a question about the right shift microcode. How do you implement that one? Since we didn't have a right shift component in the ALU.
The right shift is not any different from, say, add or subtract. You just specify the operation, the ALU operation. I think that's number 2.
We have a right shifter in the ALU.
I believe so.
We have a right, yes, we do.
So, okay, let me open up the the ALU circuit. So within the ALU circuit, there is a right shifter. So with the right shifter, the top one is XX, and then the bottom one is YY. The only difference is YY, we only use 3 bits out of the 5, because when you have 8 bits as X, you can only shift up to 8 times, which can be specified in 3 bits. And in logic sim, the right shift operation can only be using 3 bits as the input when you only have 8 bits as the number being shifted. So I have to toss away all the other bits as a result. Okay. Any other questions? No other questions. All right. Do you guys want to go through another example? No? Okay. So next week, next Monday, we're going to have our second exam. And the second, sorry? Tuesday. Oh, right. Okay. So next Tuesday, we're going to have our second exam, and it's going to be pretty much all on the toy processor. Okay. So you probably want to bring your own notes. Okay, because I don't want to have to print 30 copies of exactly the same thing, but without your annotation. So my recommendation is to print out your own copy of the processor design, and all the components, which only has 2. Okay, we only have the register bank as a subcomponent and the ALU as a subcomponent. So print out those, and bring it with you. But don't just print it out and bring it with you, okay? Because what you might want to do is to annotate, okay? Add your own annotation to the diagram so that you can explain to yourself, what does this mean, what does that mean, what does that do, and so on. Okay, so that's a good process of studying for the exam. Yep.
So if we're using that, are we gonna never mind. Probably not. The question doesn't make sense. Like, our answer's gonna have to be in binary or hexadecimal.
As long as they are representing the same thing, and you clearly indicate what base is in, when it does matter, I can accept, either binary or hexadecimal. Okay. So I can think of a few forms of questions that I can ask. Okay, I can ask you to implement, let's say, a new instruction. Okay. So what kind of new instruction are we talking about? What do you think? So let's take a look at the instructions that we currently have already implemented. You can bring my programs too, okay? So opcodes.tar.gz, every single source file in that thing, you can print it out and bring it with you, okay? It's not a problem. The only thing you cannot do is run those programs during the test. And I was about to talk about what? Oh, implementing the instructions. So my My brain is a little bit slower today. Slower than usual. It's slow to begin with. All right, so these are the instructions that we have currently implemented. I did not implement every single instruction in the spreadsheet, but the files that I provide in the drive does have all the instructions implemented. Okay. So what else do you think that we might want to implement? What about something that is a cisc that has a cisc taste to it? In other words,
Multiplying something? Like multiplying something?
well, multiply is a little bit harder to do with microcode.
Let's not go there, Shane. I didn't want to go there.
But we can do something more like this, okay? You know, we can say, we can have an instruction that has multiple slices, where the first slice is to always use register A, okay? And say A gets A minus 1, okay? A minus B. And then the second slice is the same thing as a JZ instruction, or PC equals C if and only if Z equals to 1, okay? In other words, we can combine these two. Okay, let me scroll up so people in the back can see what I'm talking about. So we can say, okay, we want to combine these two as one single instruction. How difficult do you think this is going to be? Not very difficult. Why not? We already have the slides for something like this. Maybe not exactly like that, but very similar. We already have the slices for this one. So you just take those two slices, put it next to each other, and then have a 2 followed by all zeros as the third slice. You're done with this, what we call the cisc instruction. But the point is, it is still a cisc instruction because we could have gotten away without that instruction. Because we already have instructions that can just do a subtraction. We already have an instruction that can do the conditional branch based on the Z flag. So this instruction is really just what is the advantage of implementing an opcode that can do both as one single instruction? What is the advantage? Sorry?
Lazy programmers?
Yeah, the programmer doesn't have to specify as many opcodes. Okay? But to be more exact, you were right about a lazy programmer, but it is a lazy assembly language programmer. Because if you program in C, the compiler takes care of it. You just specify the high-level operations, the compiler takes care of it. So it is not really beneficial other than assembly language programmers can now specify fewer instructions. There's one other advantage to cisc instructions, especially when RAM is expensive. Yep.
Does it keep the heat down, or is that?
It would not keep the heat down in this case because, well, a little bit, okay? Because you're not accessing memory as often because now you're reading one single opcode and it's performing multiple operations as a result. So it does lower the heat generated from traffic with memory, but within the processor, you're still exercising the same circuitry, even compared to having these two as separate instructions. So the gain of, the energy efficiency gain is not that much. Yep.
So it just takes up less space in RAM?
It does take up less space in RAM, so that's a very good observation. It does take up less space in RAM because reading one single opcode now perform more operations. Okay.
So that means it's faster because the RAM is super far away to go to. Well, it's not far away to go to.
That is correct. It is
further.
faster. Yep. It is faster when you are looking at a single processor. Yep.
Does anyone get a giant microcode ROM and implement tons of these into their hardware?
You mean in actual hardware implementation?
Yeah, like they make a bunch of different instructions that like that one.
That is a good question. Okay, so the question is about, do people do this in actual processors? Is that kind of a fair?
Yeah.
Okay, rephrase of your question. So we can take a look at the i5, okay, Intel microcode, and see what we can find here. And we can take a look at images because that's, well, it looks like something very similar to what we are doing.
There's probably a point of diminishing returns with the cis instructions.
Say that one more time.
I said there's probably a point of diminishing returns with the cis instructions.
Yes, absolutely. These days, microcode in a processor can be updated. Now, I don't really know the mechanism of how it is updated. Does anyone know how it is updated? Nope? Okay. But what we are seeing is, basically the microcode is kind of like what we're dealing with. It's just a really long bit pattern. And in this case, you can also see that the microcode of the Intel i5 M460 processor has certain parts here. They are color coded. So the red one is the microcode revision number. There's a release date. So these are all stored either in a file to be uploaded to the processor, or it is actually inside the processor itself. And somebody's trying to figure out, reverse engineer, these codes here. So they're comparing versions of the microcode between revisions, and they find all the differences and try to use the differences to figure out, what the rest of the code is for. So I'm pretty sure Intel did not actually publish the microcode format or how, what each bit is controlling. So somebody was actually trying to figure out, how it all works based on revisions of the microcode and look at the bug fix and look at the actual changes. So they're trying to figure out, okay, so from here, can we figure out what bit is controlling which aspect of the processor? But it seems to me that actual processors follow use about the same kind of mechanism, having a big ROM table to store all the microcode, and then just have the music box mechanism to kind of walk through the slices, just like the one we do. Except they're much more complicated because the Intel processor has multiple integer ALUs and multiple floating point units and stuff like that. So it's far more complicated than the processor that we are dealing with. Okay, good question. Anything else? Anything else about microcode and the opcode of the toy processor that you want me to go over? What if you look at an instruction and you go, okay, I really don't understand how this works. Okay, so I'm going to use one example. Okay, we'll go to the one instruction that is the most confusing. Okay, let's see which one is the most confusing. Okay, this is a list of all the instructions that we have so far implemented, and also all of these are now implemented in opcodes.tar.gz. So every single one is now implemented. Okay, any questions about no-op? What it is, what it does, and what happens when we execute this particular opcode. Are there any questions about no-op? Okay, it stands for no operation, which implies that when this instruction or when RAM has this particular opcode, it just doesn't do a single thing. It moves, and then it moves on to the next instruction. Okay, but it doesn't really do anything. The next one is halt. Okay, any questions about this particular instruction? It's not showing you the microcode, but I'm just asking, when we execute the halt instruction, what does it do?
Stops the program.
It stops the program. As the name of the opcode implies, it stops the program. So this is, this makes sure that we cannot go past the end of a program and start to execute in the space that is reserved for variables and data. Okay. Very good. What about this one? Are there any questions about this particular opcode? The constant part is 0 and 0, 1, which is a 5, and then we have x, x, y, y specifying 2 registers. What does it do? When the actual quote-unquote C code is x equals y, what do you think it's doing?
Assigns a register to another register.
It copies register y to register x. Okay? Register y can be any one of the 4 registers, and register x can also be one of the 4 registers. Now, in class, okay, we talked about how it is a waste to have a equals a because there's nothing to gain implementing this particular opcode. 0, 1, 0, 1, 1, 0, 0, 0, 0 is a useless opcode. Okay, I can implement it. It's no problem. Okay, I can have register A as output 0 of the register bank, route it back to the input of the register bank, and say, hey, store this into register A. Well, other than generating a very minute, amount of heat, what else does it do?
It's a placeholder.
Sorry?
It ends up being a placeholder.
But we already have no op. If I really need a placeholder, we have no op already. So this is not really particularly useful because it has absolutely no side effect. Okay, it doesn't change the flags because it's not a calculation.
So
It
are we
doesn't
not
use.
gonna implement it?
Sorry.
Are we just gonna leave that blank?
That's why I use a question mark here to basically say, okay, maybe later on we can reuse this opcode for something else. Because this instruction is useless. Yep.
It's useless, but don't we want to implement it? Because what if somebody uses it nonetheless?
Okay, that's a very good question. So the question is, what if somebody else, is using this opcode?
And it's
And
not
this
implemented.
is the job of the assembler to point out and say A equals A is not implemented, and this instruction does not do a single thing. But that's a very good question. But when we are pressed for opcodes, because I want to fit every single opcode into 8 bits, so if we end up running out of 8-bit combinations, we can reuse this 8-bit for something else. Yep.
Well, wouldn't that kind of screw up our XXYY scheme?
It would make it less general, but basically we are saying out of the 16 possible variants of this particular instruction, 4 are not actually implemented. And the opcode, the binary opcode of those 4 can now be used for something else. Okay. But the way I implement it in my C files is I have A equals A, B equals B, C equals C, and D equals C. Even though they don't do it.
At this point, it'd be just an organizational thing.
It is an organizational thing. It is also the optimization of how we make use of the opcode. Now, because it's a RISC architecture, I really suspect that we will not run out of opcode, because that's the whole idea. We want the minimum number of opcode possible in order to be able to implement every single algorithm that we can think of. Okay, and I think either we have already everything that we need, or we are pretty close to having everything that we need. What about the next one? Okay, so we are getting to the ones that are slightly more complicated. For instance, this one. Are there any questions about what this opcode does, and also how it is implemented? Okay, first of all, what does it do? What does it do?
It sets the.
It does not set anything. It checks something first, right?
Checks to the L flag.
Okay, it checks the L flag. If the L flag is a 1, then it will use register X specified by these 2 bits, XX, and it will just copy that register to the program counter. Yep, go ahead.
Would you ever use that by itself, or would you generally have another opcode before to set a register equal to something?
That's a good question. So the question is, do we generally just use this all by itself, or do we usually have something else before this? And the answer is we usually have a compare before this. But not necessarily as the one immediately before that. Because one single compare will set all 5 flags, okay? Even though we technically only have 4, but for convenience, we have the 5th one, which is the L flag, which is the one that we are highlighting right now. So typically, you would have a compare first, and then after the compare, you would have any number, at least one, of these conditional branches. Because occasionally, you want to not only look at the L flag, but also the Z flag, for instance, because you're looking for less than or equal to. Then you need to look at both.
Then you would also want to put something specific into register X. So you would jump to a specific.
That is correct. Yep, exactly. The branch destination has to be in register X, before you execute this instruction.
Otherwise, it would be kind of random when you just jump around.
Then we'll jump to wherever that register is pointing to. Yeah, that would not be good. Yep. So are there any questions about this one? No questions? Let's go ahead and implement a particular program, shall we? Let's implement the logic to find the absolute value of a particular number. Is that okay? All right? Okay. Okay. So we're going to use a new document here. I'm starting to really like doing this because this means whatever document I'm creating, and typically it should. It's not asking me whether I want to. Okay, I think I know why it's doing this, because I have to create the document in the folder to do this. But since I'm not signed in using that, Oh, okay, I see. There we go. I just have to change my identity. And now we can say new in Google Documents. And click yes. There we go. So this program is now created in the folder where you have access already. Okay, how do we find the absolute value of a signed integer? Okay, all right. So, come on, guys, you know that. But but it's conditional. You don't want to always change it. And you're not only changing the sign flag either, because if you just change the sign flag, the value will not be correct. You need to use 2's complement. Or something like that, okay? So we'll take a look at how to do this. Okay, so we'll say we have an integer, int 1 as a label, and we'll do a dot byte 0 to mean that we are going to allocate 1 byte to represent this, integer 1, okay? And this is going to be done at the very end because when we reset the processor, execution always starts from location 0. So we want the program to start from the very beginning. Okay. So now we start with the C code here. So this is basically equivalent to, okay, let me start with the C code first. We'll then convert it into assembly code. So this is equivalent to int 8 underscore t as an integer 1, okay, in C or C++. Int 8 underscore t is a type that is defined in stdint, standard integer.h, the header file, which basically means int 1 is an 8-bit signed integer. Okay, why do you think I want signed integer in this particular example? Exactly, because if it's unsigned, then the absolute value is always just the integer itself. Okay, because it cannot go negative. Very good. Okay. So then we want to specify the logic. This is not inside the subroutine. We do not have local variables. So all of these are kind of global variables. So we say if int 1 is less than 0, then we have something to do, because if it's not less than 0, we just let it be. Is that making any sense? Okay. So if it is less than 0, and I want int 1 to store its own absolute value, I'm just flipping the sign so that it is non-negative. What should I do to int 1? Sorry? Bit shift. Why would I need a bit shift?
Can you subtract it by itself twice?
Okay, you can do that. Okay, so there are a few ways to do this. Well, okay. When you say subtract itself twice, you have to be clear about how it is done. Okay, let me show you why I said that. Okay, you can say this is int 1 minus int 1, and then do it one more time. Okay. Okay, so what is going to be the result of these two operations? These two statements?
0.
0, very good, because the first one is guaranteed to be a 0. Anything minus itself is 0. So then I'm subtracting 0 from 0, which is always 0 as well. So this is not going to take the
You
absolute
need to
value.
save the value. So you need to say like,
Okay, we can do it in a very complicated way, like that, right? That's going to work. But that's a very long way of saying something that's easier. Let's apply algebra here. Isn't that saying the same thing as just that? Okay, which is implicitly that. Is that okay? No, this is a regular, we don't have a not here. This is a subtraction. So it's not a bitwise not. Okay, so this is one way to do it. There's another way to do it. Okay, we can use 2's complement. Remind me again what is 2's complement.
flipping all the bits.
Flipping all the bits, which is called 1's complement or bitwise not, and then add 1 to it. Very good. Okay, so we can also say something like this. Int 1 is the tilde version of int 1, which is a bitwise not. Okay, and just to make sure that the order of operators is specified very explicitly, we can do it like this. Okay, so these two statements will end up doing exactly the same thing, because 2's complement is negation, is arithmetic negation. Is that okay? which one do you want me to use to implement this particular program? It's up to you. If not,
Second one.
how about we do both? Yeah. Okay, we will do both. Okay. Okay. All right. So this is the logic that we want to implement. Okay. So the next stage is to look at this and go like, we don't like structured code in this class. Okay. Because you get enough structured code from Mr. Fox and Professor Fox and Professor Subsidiary. Okay. So in this class we can go unstructured. Okay. So when you go unstructured, you want to invert this logic here, and you're looking for greater than or equal to, so they can go to a label that is indicating, oh, let's skip all this stuff, okay, and just go straight to L1. Is that making any sense? So when you compare this version of the program compared to the earlier version, logically speaking, do they do the same thing? They do exactly the same thing. Oh, by the way, do we still need these curly braces to indicate this is a block statement? Nope. Because what is the statement embedded into the conditional statement? Because every time you see if there's an embedded statement, what is embedded into the if? The goto, exactly. The goto is the only thing embedded into the conditional statement, which means this entire block here does not even belong to the conditional statement anymore, and as a result, there's no use of the curly braces. So I'm going to remove the curly braces, or just braces. There we go. Okay, this is our second version, and let's take a look at the third one. Now, just keep in mind that we cannot do both at the same time, because if we do both, then we are negating it back to the original version. Okay, so when we actually implement it, I will have to say, okay, pick one of these two. Okay. Now we look at this and go like, well, let's see whether we can do all of these things kind of easily in assembly. This looks like not too hard. Okay, we just have to do a compare and then the conditional go to. This one is not too hard. We have two. We just need to put 0 into a register, and then put int1 into the other register. We don't have a single instruction that can do this, negation, but we can use 2 registers to accomplish the same thing. And this one is not too difficult either. We already have a bitwise NOT. We know how to add 1 to it because it does require the use of 1 more register, but we can do this, not a problem. Okay, very good. So now I think we are ready to implement everything in assembly. Okay, so when we implement everything in assembly, the first thing is I'm just going to move this all the way to the end. Okay, Control X, Control C, and turn this one into just int1 dot byte 0 to indicate that we want to reserve 1 byte in memory so that we can store the value of int1. Is that okay? So dot byte 1, dot byte 0 is really just saying, okay, reserve a byte in memory. Initialize it to 0 originally, and the label int1 is the address of that byte. Is that okay? Okay. I better specify a halt instruction here to stop the program so it doesn't run into the variable itself. Okay. Okay, what about this part here? Okay, if I am going to implement this particular part or this conditional statement that is in C, how do I do it in assembly? We need to compare to 0, okay? And whenever we compare, I have to compare only registers. So that means the 0 has to be stored into a register first before I can compare. Int1 is also not in the register, so I need to put int1 into a register as well before we can compare. So we have some prep work to do before we can do this. The prep work is actually more complicated than it seems, because we need a, do you guys want to use the LDI instruction, or do you want to use the other notation, which is a equals star tc++, and then we use comment to specify what is next to it? LDI? This one? Okay. We can use both, okay? I can work with both, okay? Okay, so the first one is to use this one, and I'll give you an alternate representation, which is LDI, the register being changed, and the value that we are going to use to change it. The value that we are using to change A, register A, is int1, not the content at int1, but the address itself int1. So we're using the value of the label, not the value at the label, to initialize variable a. Is that okay? Does everybody understand what that means?
So we're running the address?
So this byte is sitting somewhere in RAM, right? Anything that is in RAM has an address. int1 as a label is representing the address of this byte, not the content of that byte. So when we say LDIA int1, we are using the address we are storing the address into register A, not the content at int1. Is that part okay? Okay. So we need another register to store the 0 because we need to compare to 0. So we'll just pick register B for that purpose. So we can say B equals star BC++. In this case, it is a 0. Or if you prefer the other notation, it's LDIB with a constant of 0. So now we have set up register A and register B, and it is time to do the actual compare. When we do the compare, we can choose to compare it like this, A minus B, or we can choose to compare B minus A. In this particular case, we are branching when int1 is greater than or equal to 0, and int1 is signed. So one way is usually better than the other one. We just have to figure out which one. Yep, go ahead.
Don't we need to load in the value that's stored at int1 of the address? Because right now A is holding the address of int1, is that correct?
Yes.
So we need to actually...
Oh, we need the
Yeah.
content in order to compare.
So
That is
you
correct.
right.
Yep, you're right. Okay, I forgot about that. Because A has the address of the byte that we want to compare, not the content, and we want to compare the content, we have to get the content at that location, so we need this one, which in mnemonic is LDA with indirect A. Okay, the parentheses indicates indirection, which is the same thing as asterisk. Okay,
And we-
very good. Yep, go ahead.
We can't just LD into 1 into A?
No, because because we don't have an instruction to do that.
Oh, okay.
And in addition to not having an opcode to do it, the processor architecture actually has no internal pathway to do it either. All right, so we can do one of these two compares. So the way we choose this is to look at the polarity of the compare and say, okay, when do we want to branch? Okay, we actually need a third register to store L1, which is the destination of the move. But we can do that later. Okay, we don't have to do it right away. We can do the compare first and then load the other register. But just in case I forget, let's do that first. So we can now say register C. Okay, we pick the next available register to be L1, which is the address that we want to branch to when integer 1 is greater than or equal to 0. Okay, so the actual, okay, this is not the right notation. So the right notation is this. And then the mnemonic to do that is LDIC L1. There we go. All right. So depending on which way we compare, we can simplify the conditional branch by a great deal. Okay. The instructions that we do have in this case that are relevant is JL, okay, jump if less than, or we also know it as PC equals C if and only if L is 1, or in mnemonics we can say this is JZ or JL using register C. So given this is an instruction that we have, and then the other instruction that we also have is based on the Z flag, right? Okay, so we can say PC equals C if and only if Z flag is a 1, or using the mnemonic version, it is a JZ C, like that. Okay, so given that this is the preferred way of doing things, okay, if the result is greater than or equal to, or I should say less than or equal to, we want to do it like this. How should we do the compare? Should we say A minus B, A being the content of the variable int1, B being 0, or do we want to do it the opposite way? we are looking for something, if A is less than or equal to 0, then we don't want to branch around. So it should be the other way around. If 0 is less than or equal to A, then we want to branch around. Is that okay? So that means, which way should we do the compare? Which one has 0? Tell me, which one has 0?
B minus A, right?
B has the 0.
Would you do A minus equals B? No.
Now B minus A is correct because when
If you get a carry
0,
so if you put no, because if it equals 0, both 0 and then
we are branching around when it is less than or equal to 0.
We're not looking at the carry flag.
Okay, let me think about this.
What's the L flag?
The L flag is less than in the signed
The sign
way.
flag?
No, it's not the sign flag. It is the exclusive OR between the sign and the overflow flag. But the L flag does indicate the result of a signed comparison, which is what we need here. Okay? Okay, so I just have to go through these two alternatives. Okay, A minus B is basically asking, is A, which is L1, less than, if A, which is L1, int 1, if it is less than 0, we branch around. Does that make sense to you? No, it doesn't make sense to me. Okay, so I'm gonna say this is the one, and we double check. B is 0. Okay? And this is saying if int 1 is less than, B being less than or equal to A, we want to branch around. If 0 is less than or equal to int 1, we branch around to halt. Does that make sense? What is the other way to say that 0 is less than int 1? Int 1 is greater than or equal to 0. Well, if int 1 is greater than or equal to 0, it means it doesn't need to have the sign flipped, so it's okay to move on. Okay, we don't need the negation. So this does make sense. Is that okay? No?
I'm just trying to look at the L flag right there. If you see, go see if it's on the L one.
Right? What about the L flag?
So if you do B minus A, and if A is, let's say, -3, then L will be 0.
Then L would be 0. Correct.
Okay.
Then it would not branch around. But at the same time, Z is also 0 as well because A is not 0. So it would fail both of these conditional branches, and it has no choice but to execute the actual arithmetic negation code.
So on the exam, I want to know what the L flag does and what the overflow flag does really well.
That is in your ALU.circuit file. So let's go back to the circuit diagram. Okay, so it's this
I mean, it
one.
makes sense because if you do a subtraction on a negative number, it becomes positive, so the signs would change. Is that the logic behind it?
Sort of.
That the result becomes a positive?
But we're not just looking at the sign though. Yeah, we're not just looking at the sign. We have the ALU already indicated here. This one. Okay. So this is the ALU, and the L flag is one of the output. It is always the L flag. This is the L flag. The bit 4 is the L flag, and it is the exclusive OR between the sign flag and the overflow flag. The sign flag is the easy one. The sign flag is nothing more than really just picking out the most significant bit of the result. That's the sign flag. The overflow flag is a little bit more complicated because the overflow flag, which is O out here, it depends on whether we are adding or subtracting. So based on whether we are adding or subtracting, the way we compute overflow out is different. So that's so that is something that you have to look into, but it is all defined in the ALU circuit itself. So what you need to do when you study is to look at the ALU design and make sure that you understand every single aspect of that particular design. And annotate when you need to. Yep.
I'm just trying to catch up a little bit. What is A equals star A?
It means we first use A to dereference to a memory location, grab the content at that location, and then use that content to update A.
So we didn't already do that with the first instruction?
Nope. The first instruction just loads the label itself into A, which is, the label is representing the address of the byte, not the content of the byte.
Okay. Although we did load the content of something in RAM, the content of something in RAM was just another location in RAM.
Say that one more time.
Because the A equals star PC plus plus is us taking
They put an address, the location into register A, and then A equals star A takes what's in register A, that address, it goes to that address and takes the content of it.
Okay, maybe when we assemble the program, it will be clear what we're dealing with. Okay, yep, go ahead.
What are you using JS work the same like what we have right now with JS?
No, it would not be the same because JS does not deal with a situation where we have an overflow situation.
Would that
Whereas JL does. It does not, well, okay, you're right, because in the case of comparing to 0, you would never have an overflow. So JS would be the same as a JL. Because when overflow is a constant 0, then when O is a constant 0, then the exclusive OR between sign and overflow is the same thing as as sign itself, because the other one is a constant 0.
Okay, so this is the one case where it's the same.
Yes, but you don't want to use or abuse the equivalent instruction because in general, when you're dealing with a signed comparison, you should use a JL. It's just that in this very specific case, using JL versus using JS would end up doing the same thing, but only because you're comparing to 0. But when you're comparing to another general signed number, then those two are no longer equivalent. Okay, all right. But that's a good question. That's a good observation. All right. So getting back to here, are we doing okay or not? Okay. So I'm hoping that I can get to the assembling stage of this one because that's actually the kind of the more important part. So we're going to continue with this. Okay. So if I continue at this point, it means A is less than 0 at this point, okay, because that's how we can end up here. So now we want to implement this particular statement. We'll just forget about the next one because I really want to finish the assembling of this program so that we can differentiate what a label is. The label is the address, not the content at the address. Okay, so how do we do this? Okay, we want int1 to be the negation, arithmetic negation of itself, and I want to use the subtraction. Okay. What are we going to do? We already have int1 in register A, so I don't need to reload it into A. So what else do we need to do? We need to put a 0 into the other register, but B already has it too, right? Is that okay? B has 0, A has int1 already. So we got the ingredients already. So we want to do the subtraction, okay? So we want to say B minus A, which is what we actually have here, okay? But this time we want to store the result because we actually care about the arithmetic negation of this particular calculation, but we don't have a choice. We cannot say A equals B minus A because we don't have any instruction to do that. Okay? Is that okay? Because the instruction that we have is always doing something like this. But that's okay. We can just follow up with something like this because the result, the thing is, we are not really interested in storing the value in register B. We want to put it back into the variable itself, right? So it's okay to put the temporary result, which is the right-hand side, into a register B. Then we can specify it and say, okay, let's go ahead and store that back into memory. which is then followed by a, okay, we can reuse a at this point because a is no longer useful. So we can say a equals star PC++, and this time we want to use int1 as a label, okay, which in these instructions is equivalent to LDI a int1. So register A, once again, has the address of the variable, not the content. So the next instruction is to say, okay, use A to tell me where to store, and we want to store the content of register B into where A points to. In the mnemonic, this is a store operation, so we are storing into whatever whatever A points to, and the value of register B is what we use to update that location in memory.
Isn't it the reverse?
Did we use the reverse in the mnemonic? Okay, store is, well, we don't actually have the mnemonic of ST. The one thing is I just want to be consistent. In other words, what is being changed is the first operand. Okay, that's the only part that I need to be consistent. Because when we load, this is supplying the value to update this one. I just want to make sure that I use the same notation. B is used to update whatever A is pointing to. Yep.
So on the exam, do you care whether we use the right-hand side notation or the left-hand?
I don't really care because the only part is I have not really talked about all the mnemonics.
Oh, okay.
So we don't have the name of all the operations, whereas the left-hand side is something that we have been using all along. Yep. Okay. All right. So I think we are done. Okay. This program is all done. So now it's the stage for assembling. Yep. Go ahead.
Can you go over the star PC++ operation?
The star PC++ operation.
Yeah, just in general.
So this particular operation has one opcode and one byte after the opcode. Okay, the opcode itself is okay. So so let's say we are using this one. Okay, so the opcode itself is 6C in this case. It takes up 1 byte. When we execute this particular opcode, the microcode engine will execute whatever the slice will basically specify that say, okay, whatever the PC points to, which is 1 byte past the opcode, let's grab the content of that byte and store that into register A.
Opcode is in RAM, right?
Opcode is in RAM, so we have 1 extra byte in addition to the actual opcode itself, which is representing the value that we want to overwrite the register with. Okay. Yep.
Your mnemonic codes, can you print string with coding? Mnemonic codes.
Mnemonic code?
Yeah, here. So I'm slightly confused with flag L. So after arithmetic operations like 0 minus some negative number, what exactly flag L represents?
The L flag.
L flag. L equal what? So it's represent what the result is like.
Okay, so to answer that question, I think I understand your question here. So the answer to the question, okay, so let's see how we can track this down, everything from the logisim file. Okay, this is the logisim file, and when you look up the opcode of the jump, if and only if L is 1 opcode, it will tell you that PC mux is going to look at this particular flag. Is that okay? Which is a 4 for that particular PC mux. Okay? Now, okay, this is also going back to, okay, let me find the window that actually has that file. There we go. Processor. Okay, so when we look at this file, send off. There we go. So when we look at this file, PC mux is this particular value, which is a 4. Is that okay? Okay, so given PC mux is a 4, it means this PC mux is a 4. This is 0, 1, 2, 3, 4. So we are paying attention to bit 4 of the flags register. Is that okay? All right. But how did we get bit 4 into flags? I mean, how does it store the value? Flags is getting its value from flags out of the ALU. Is that okay? So now we switch to the ALU here and say, okay, what is the 4th pin of the output of the flags? Okay, so the 4th pin of the flag, which is this one here, is the exclusive OR between the sign flag and the overflow flag. Okay?
Is that the, are you talking the 4th pin as in first, second, third, fourth, or 0 first, second, third?
0, 1, 2, 3, 4. So this is pin 4. Okay, that's probably the better way to say it. So pin 4 is coming from the exclusive OR gate, and the exclusive OR has the input being the sign flag and the overflow flag. In other words, L is sign exclusive OR with overflow. And when we talked about the sign flag and when we talked about the assigned comparison, we said, okay, this is the indication of the result of comparing two signed numbers.
Okay, when you compare it to signed numbers, so L become 1
When the number on top is less than the number on the bottom.
okay, when L is less than second.
In other words, when you look at signed number comparison or signed number subtraction, A minus B, okay? If the L flag is a 1, it means it is equivalent of saying that A is less than B.
Okay, that was my question.
Okay. But the actual mechanism that makes it work, we actually kind of talked about in class 2. So you might want to, kind of keep that, as one of the resources that you want to bring with you in the exam.
Second question. Work with unsigned numbers.
Say again?
With unsigned numbers.
With unsigned
The
numbers.
same,
Okay, so with unsigned numbers, how do we know that A is less than B?
yes, with sign flag.
No. Okay, so what do we use here for unsigned comparison? There's one flag that we can use for unsigned comparison. The carry flag, because carry is borrowed. What does it mean when you need to borrow?
It means the number before is 0.
Okay, how many dollars do you have in your pocket? You don't have to tell me the actual number. You don't have to tell me the exact number. Okay, give me some bogus number.
$7.
$7. Okay. So 7 is A, right? Unsigned number. Okay. We cannot carry a negative amount of money because we are not the government.
We carry that all the time.
Okay. So we can only carry non-negative values in terms of currency, right?
Yeah.
So Shane has got $7, and I'm specifying B, and I go like, Shane, give me $10.
I ain't got it.
Borrow it from somebody.
Let me get $10.
So that's what a borrow means, right? So Shane needs to borrow because he doesn't have enough money.
But I can't borrow $3. I gotta borrow the whole 10.
Yes, exactly. When you borrow, you have to borrow the whole of the next digit. So in hexadecimal, you're borrowing 16. In base 10, you're borrowing 10. In base 2, you're borrowing 2.
Good thing I have a $10 bill.
Dang.
Is that explaining why in unsigned comparison, the borrow flag, which is also known as the carry flag?
How to work with borrow flag with unsigned. But my question, can I use L flag with unsigned comparison?
No, because in the case of unsigned numbers, the L flag itself does not always indicate the correct ordering.
Okay.
It will work right when A and B are both non-negative, but if one of them is negative, or if one of them has a most significant bit of a 1, then it won't work correctly anymore.
So
Because
L
they
flag is
will
only
look at the
for
negative number as a
signed
bigger value.
comparisons.
And then the carry flag only for unsigned comparison. Okay, so I'm not done with the program yet. I'm going to take this to the lab and finish it over at the lab. And because I also have the implementation of all the opcodes, we can actually test it this time. We can actually run it through the simulator and see it work. Woohoo!
Why is canola written on the board?
because I was trying to explain to